Ohm's law tells us there's a relationship between voltage, current, and resistance for ohmic materials such as metal wires. Now when it comes to metal wires, they have a conductivity represented by the Greek letter sigma and defined as the current density in relationship to the strength of the electric field in the wire. Resistivity is the inverse of conductivity. And the R in this equation for Ohm's law says resistance is equal to resistivity times length divided by area, meaning for ohmic devices like long metal wires, their length and their cross-sectional area, along with what material they're made out of, all factors together to give an indication of the resistance. When it comes to a light bulb, there's a very small bit of resistance in these posts. They are made out of somewhat skinny or thin wires, but the vast majority of the resistance is in the filament, which is a much skinnier wire. And in fact, it's a very long wire. It's often coiled up, so there's a lot of length that fits into a small space. I often draw a picture of a light bulb like this. So one of these metal posts comes off of the metal case that's actually threaded into the socket. And then there's a insulating material right here, and the other post comes off of here. And then the filament is this very thin wire that's often coiled up, so you can fit a lot of length in a short region, and that's where most of the resistance is when a light bulb is placed in an electric circuit. Now, when do these light bulbs usually break? If you ever noticed it, a light bulb generally doesn't burn out after it's been on for a long time. It's usually right when you switch on the light that it burns out. And this is due to thermal stress. See, there's a relationship between resistivity and temperature. We say resistivity is a function of temperature. And that function looks something like this. Resistivity is equal to some standard value of resistivity multiplied by 1 plus this constant alpha, which stands for the temperature coefficient of resistivity. So 1 plus alpha times T minus T standard. Let's try to get some insight into that equation without deriving it, at the very least. Explain it. Well, first of all, even superconductors have non-zero resistivity. They have a very low value, but if you make a graph of resistivity versus temperature, you'll never find a zero value. In other words, our graph does not include the origin as a data point, because that suggests you can have a zero value for resistivity. Even the best conductors, superconductors, still have a non-zero resistivity to them. Okay, so for a metal wire, the graph might look like this. So let's just pick some point, any point really, right here. We'll say that there's some reference value of resistivity at that reference temperature. If we pick a different data point, then that's a higher temperature T and a correspondingly higher resistivity rho. So this value of rho is equal to the reference value of resistivity times, well, you see the equation, 1 plus a constant called the temperature coefficient of resistivity, and then multiplied by whatever higher temperature minus the reference temperature. So it really is just another form of the equation for a line, right? Now, because we have different temperature scales that are kind of arbitrary where they put the 0 in the Fahrenheit scale, we choose to put the 0 below freezing, whereas the Celsius scale puts the 0 right at freezing. So depending on what temperature scale you have, you could shift the y-axis to the right or to the left, and we can still graph resistivity, and the graph is still some straight line. So whatever you choose as your reference point for resistivity just has to match up with whatever reference point you have for temperature, right? Okay, but any 2 points along this line, a reference point for temperature and a higher temperature, have a corresponding reference point for resistivity and the higher resistivity at the higher temp. Now, what does this have to do with thermal stress and light bulbs? Well, because resistance is equal to rho times L over A, then we can make the same equation and say, as resistivity goes up, so does resistance. And so the same equation can be expressed. We can say resistance is equal to a reference value of resistance times 1 plus alpha times T minus T naught. After all, we could just take both sides of this equation and multiply by L over A. And so this rho naught times this L over A is this R naught. And this rho times the same L over A is this R. Okay? So resistance goes up with increasing temperature. So we turn on the light bulb by dropping a switch. So the light bulb is represented by the symbol for resistance. There's the voltage. The switch is dropped. And at first, this wire, or the filament, is at room temperature. And so its resistance is really low. So we'll say this represents room temperature. That's our value of T naught. And so the resistance value is pretty low at that point. But after that switch has been dropped for a little bit and these electrons start to drift, by the way, we know the electrons don't actually come from the battery. They were already there in the filament, right? Remember, these electrons drift with a speed of about 10 to the negative fourth meters per second. But it's as soon as we close the switch, the light bulb begins to glow almost immediately. So we're not waiting for electrons to come from the battery and make it into the filament. They're already there. Closing the switch just creates the potential difference that makes the electrons in the connecting wires, in the post, in the filament, in all the points start to drift. And as they drift, they collide with the impurities. So here's an electron, and here are these impurities in the wire. The electron collides with one, and energy is converted from kinetic energy to thermal energy, right? And so that causes the filament to start to heat up. And so the temperature gets a little bit higher, and the resistance then gets a little bit higher. This all happens very quickly. This is not a slow process at all. There's a rapid increase in the temperature as the current develops. That current produces several collisions that produce the thermal energy that increase the temperature, and so that rapid increase in temperature causes thermal expansion of the wire. Now, we open the switch back up, and then the current goes away, but the vibrations of these molecules, of these impurities, doesn't instantly go away, right? there's a very gradual return to room temperature as heat is radiated away from the light bulb. So there's a rapid thermal expansion when the light bulb is first turned on, but a very gradual thermal contraction back to room temperature. And so imagine you can do your own experiment. Go into any room in your house, and if you have an incandescent bulb, I know most of our light bulbs now are LED anyway, but I'm sure you have some incandescent bulbs that have a glowing hot filament. Just flip the switch on and off, on and on, on and off, on and off. At some point, ultimately, that filament is going to reach its final breaking point, and it's going to happen right when you turn the switch on, not right after you've turned it off, because that rapid growth in the current makes for a rapid increase in temperature, which makes for a very rapid thermal expansion, which causes a large amount of thermal stress.